All right, so for a super quick review of everything we've done so far, we have been dealing with derivatives, which another word for that's differential calculus. And this was the solution to the tangent line problem and all of the things we could do from there. We calculated derivatives in a lot of ways. We applied doing optimizations and curve sketching and all that stuff. But the solution to the tangent line problem was, how do you find the slope of a curvy line at a point? And what we did was we started by making a secant line, and then we just let that point get closer and closer using the limit process. Remember, the limit as delta x goes to 0, because we can't really shrink it down to where it's just one point, because then the slope formula fails. But we could take the limit as delta x goes to 0, and end up with the slope of the tangent line. Our new problem is called the area problem. And our goal is to figure out what's the area under a curve, under a graph, under an equation, from point A to point B, all right, and all the things that will allow us to calculate. And we can't just use our old geometry area formulas, because this is not a shape that you have a formula for. It has an odd shaped top depending on what the function is. So we're going to start today with this process called Riemann sums, which is our first attempt to solve this area problem. All right, so here's an example problem. What's the area under the graph of x squared plus 1 from 1 to 3, x is 1 to x is 3. So here's a picture of the area I'm looking for, and it's a little distorted. I stretched it out sideways so you could see all of the area, because this graph gets a little steep. But this shaded in area is my goal. How much area have I enclosed? And the reason this is a challenge is because the top is not a straight line or some sort of shape that I've dealt with in geometry. It's part of a parabola. So here's our first attempt to find this area, and it's called a right-hand rectangle method, a right-hand rectangle Riemann sum. So our strategy here is to break this shape up into pieces that you can find the area of, and in this case we're going to use rectangles. My first rectangle, all right, I'm trying to deal with the region from 1 to 1.5. 1 is the left-hand side of that interval, and 1.5 is the right-hand side of that interval, obviously. The way I'm going to get an approximation for that area, the green shaded area between 1 and 1.5, is I'm going to go to the right-hand side of that interval and figure out how tall the graph is right there, and that's 3.25. I'm going to create a rectangle by going up 3.25 and straight to the left to the other side of the interval, and then straight down. That rectangle that I just drew has dimensions of 0.5 and 3.25. 0.5 is the distance from 1 to 1.5, and 3.25 is the number I get when I sub 1.5 into the equation x squared plus 1. Now, that's my first approximation. That's the approximation of this area. And the reason it is good is because it's a rectangle. I can find the area of a rectangle. The reason it is bad is because it overestimates the true value by this much. That red area is part of my sum, but it is not part of the actual area. So there's the give and take. We will figure out ways to make these approximations better as we go and eventually make them perfect. But for right now, I'm going to use this rectangle, just realizing it's wrong by that red amount. The second rectangle I'm going to get by going from 2 straight up, straight across, and down. So I'm creating a rectangle. It is a 0.5 across the bottom. And the right-hand side, I'm plugging in 2 to the equation. When I plug in 2 to the equation, I get 5. The next one is based on 2.5. It's 0.5 across the bottom, and it is 7.25 units tall, because when you plug in 2.5 to the equation, you get 7.25. And the last one is 0.25 times 10, because of this last rectangle would be 10 units tall. So at every step of the way for a right-hand rectangle, you're going to use the right-hand edge of the interval. You're going to go up to the graph, across, and down. Again, this is good because it's 4 rectangles and I know the area of those, but it's bad because all of this red area is going into my sum, but it shouldn't. I'm overestimating by that much. But let's just add them up. 0.5 times 3.25 is 1.625. 0.5 times 5 is 2.5. 0.5 times 7.25 is 3.625. And 0.5 times 10 is 5. If I add all of those together, I get 12.75, which is my right-hand rectangle estimate with 4 rectangles of the area under this graph from 1 to 3. All right, so I want you to try to pause here and use your intuition. And if we just did a right-hand rectangle, see if you could do the left-hand rectangle. Look for any similarities and differences. All right, so pause this. Try this left-hand rectangle estimation of the area. Okay, so our first rectangle on a left hand is 0.5 units across the bottom. But again, this is in a left-hand sum. I'm going to use the left-hand side of this interval. I'm dividing up my 1 to 3 into 4 subintervals. So this first one goes from 1 to 1.5. And on a left-hand interval, I'm going to go up at 1, straight across, and down. So this rectangle is 0.5 by 1. My second rectangle is 0.5. Excuse me, that's not by 1. Take that back. My first rectangle is 0.5 by 2. Because if I sub 1 into my equation, I get 2. My second one is 0.5 by 3.25. What you notice is the area of my second left-hand rectangle, the 1.625, that was my first right-hand rectangle. It's just that the 3.25 on my last screen went this way, and on this screen it goes this way. So those two rectangles have the same area, it's just that it's an underestimate of the second region in the left-hand sum. Okay, so then my next one would be 0.5 times 5. In fact, these last 3 rectangles were all part of my right-hand sum, and I'm leaving off the last one. My fourth rectangle, there was my third one, 0.5 times 5. My fourth one is 0.5 times 7.25. So if I add those together, I'm going to get 1 plus 1.625 plus 2.5 plus 3.625 and get a total of 8.75. So again, this is an underestimate. This is my next shot at summing up this area under the curve, but it's underestimating by this much. So I've got one sum that was significantly too much, one that's significantly too small. My next goal is to find one that's a little bit better. But before I do that, remember these 3. Remember my last sum was 1.625, 2.5, 3.625, and 5 because I used that last one. So from the right-hand sum, I kind of moved that last one off the end and scooted this 1 to the top of the list. So you're going to see some duplications in your left and right sums. That's normal, and that should happen if you calculate both left and right for the same area. Okay, so we've seen a right hand that in this case was an overestimate, a left hand that was an underestimate. Let's try to do a little bit better job. Let's do midpoint rectangles. So to estimate the sum, and I've kind of zoomed in and added some points because they're a little bit more a little bit longer decimal numbers in this case. But to estimate this area down here, between 1 and 1.5 under this graph, I've done an overestimate by going to the right and making it this rectangle. I've done an underestimate by going to the left. So instead, let's kind of split the difference. What if, instead of using the 1 or the 1.5, I come right here to 1.25 and come up and go both left and right straight across and make that the rectangle. So can you see why this is better than both of my other options? This is going to be actually pretty close to that true area. because it overestimates a little bit over here, but it underestimates a little bit over here, and those two kind of cancel each other out. Not perfectly, but they do better than the left or the right because I've got a little bit of overestimate, a little bit of underestimate. So a midpoint is going to ignore left and right, and I'm going to get the height of my rectangles by subbing in 1.25, 1.75, 2.25, and 2.75 to create these rectangles instead of one that's fully overestimating or fully underestimating. Okay, so this first one, it's still 0.5 units across. But this one, and I've filled in for you 2.563, you're going to have to find that most of the time on your own, but you find that by just substituting into the function. 1.25 squared plus 1 gives me 2.563. 1.75 squared plus 1 gives me 4.063. All right, so second one, they're all 0.5 across. That's never going to change in this problem because I've got a width of 2 and 4 rectangles. It's just a matter of substituting in those midpoint values, 6.063 and 8.563. And that's going to be rounded off a little bit by my program, but that's definitely a better approximation because not every rectangle is fully above or fully below. Like I said, it's going to split the difference a little bit. All right, so I'm going to pause, fill this out, and be right back with the number. All right, so we're back with the midpoint sum. The midpoint sum gave me 10.626. And that fixed a lot of our problems, a lot of our over-underestimate problems. It's not perfect because if you look, like on this last rectangle, this area that I overestimated is not exactly the same as this area that I underestimated. So I'm not getting the perfect area each time, but it's a whole lot better. In fact, you don't know how to get this yet, and we're not talking about this yet, but the actual area under the curve is 10.6 repeating. So you can see that it is extremely close to our midpoint. Our over and under estimates were 12 point something and 8 point something. So those were significantly off. The midpoint solved a lot of those problems. All right, so just to wrap this thing up, how do you make the approximation better? We've got midpoint, which is better than left or right, but in the long run, that's going to be irrelevant because we don't care until it gets perfect. And in order to make it perfect, we make it better and better and better by using more rectangles. If you use a bunch of little skinny rectangles, you're going to get a better approximation than by using fewer, wider rectangles. And how do we make the approximation perfect so it's no longer an approximation? This is the part that requires the calculus. Use infinity rectangles. Now, it's kind of hard to add up infinity different things. That's what we're going to learn how to do. It's also hard to find the slope if there's just one point, but we solve that problem using limits. So what we're going to basically do is take the limit as the number of rectangles. This is not anywhere close to what it officially is going to look like, but the number of rectangles approaches infinity of the area of the rectangles. And once again, everything depends on limits. So that's how we're going to solve the area problem. For right now, just getting a head start with Riemann sums.